Welcome back. In this lecture we will look at how the maximum power will influence mainly the inverter size and its cost. The maximum power is one of the three main requirements on the operating range of an electric drive. When analyzing the electric drive and its operating range, we have not yet discussed the sizing of the power electronic inverter. Indirectly, we have just assumed that it allows the electric machine to operate in its full operating region. The size of an inverter is measured as its nominal apparent power, S inverter. Apparent power is the product of voltage and current. For alternating currents, the apparent power is the active power, P inverter, divided by the power factor, cosine phi. For a typical EV motor at high power, the power factor is about 0.8. The active power drawn from the inverter is the electric machine's mechanical power divided by the machine efficiency. The efficiency at peak power is in the order of 90%. Combining these two equations, we can see that the apparent power of the inverter is proportional to the mechanical power of the electric machine, if we assume that the power factor and efficiency at peak power to be fairly constant. The cost of an inverter is roughly proportional to its apparent power, and therefore it will be roughly proportional to the maximum mechanical power of the electric drive. So, the reason to limit the maximum power of the electric drive is not that it saves cost on the electric machine, because that cost is determined mainly by the machine's maximum torque and maximum speed. Instead, the reduced maximum power will save cost for the inverter. It is very difficult to draw general conclusions about the cost for power electronics and the electric machine for all types of drive systems. However, for the type of high-speed electric drive system which are typical in many electric vehicles, we can conclude that the costs of these two parts are similar, so there are good reasons to put effort into minimizing the cost of not only the electric machine, but also the inverter. This is the full operating region of an electric drive. In the case where the inverter is sized such that it allows the electric machine to operate in all its possible operating points. The operating point setting the highest power requirements is this point. Here the mechanical power is 393 kilowatt, which leads to a very expensive inverter. There are, however, opportunities to limit the maximum power to lower values. If the power is reduced to 300 kilowatt, the electric drive can only operate in this region. In order to allow for a smaller inverter, the voltage of the electric machine is kept constant above the base speed, instead of being increased linearly with the speed. This is achieved by reducing the magnetic flux density in the machine. As a consequence of the reduced magnetic flux density, the torque at maximum current is also reduced with speed. The result is that a smaller inverter can be used and still allow the electric drive to operate at high speeds, but at the expense of less torque in the field weakening region. Reducing power from 393 to 200 kilowatt will require about half the apparent power rating of the inverter needed to allow the full operating range of the electric machine. Notice that we are not making any significant changes to the electric machine when the power is reduced, so the only major change is that it saves cost on the inverter, while the cost of the actual electric machine remains almost the same. It is possible to reduce power even more, in this case to 100 kilowatt. Notice that the base speed is reduced when the maximum power is reduced. Here the base speed is down to about 3000 RPM. To design machines which has a wide field weakening region can be problematic though. Often this approach leads to a mechanical power output which isn't constant in the field weakening region. So often the base speed is not lower than about 1/4 of the maximum speed. Should the ratio between base speed and maximum speed be lower than that, it is likely that it would be better to use an additional gear rather than to reduce the base speed of the machine further. So, this lecture, together with the earlier analysis of the maximum torque and the maximum speed, have shown that there are three main ways to influence the operating region of the electric drive. First, changing the maximum torque, which will mainly influence the size and cost of the electric machine. Second, changing the maximum speed, which at lower speed has little effect on the machine design and at high speed requires a more complicated and expensive rotor in the machine. And third, changing the maximum power, which will mainly influence the size of the inverter. This lecture has concluded the presentation about how changing the requirements on an electric drive's operating region will influence the cost of the electric drive system. Later we will use this to determine how an electric drive can be sized to minimize the cost. But first, practice what you have just learned about electric drive and how we can influence its operating region.